Just to get started, I wanted to give you a brief overview of what our goals are in terms of neural-inspired computational engines, elements. Engines actually is referring to a specific project, but just to highlight the goals, again, this is something that has appeared in several talks, and I think it's a common theme that has been talked about throughout several workshops. What we're trying to do with these new systems is two things. One is to analyze, predict, and control natural and engineered systems in ways that we can't do with conventional computing approaches. And the other goal is to understand the physical mechanisms behind thought, basically neural systems, consciousness. And literally, this is what makes us human in terms of our capabilities. Potentially what the outcome is that from these systems is that we'll be able to predict the future based on our experiences, based on our history, in the most efficient manner possible. So, quick outline, why should we consider neural-inspired systems? Why would you want to build systems like these? I'll talk about how we're going to build these neural-inspired systems, and actually you've seen some of those already today. There are a couple more talks in the afternoon coming that will showcase some of the existing and systems in development, and conclude with what are we going to do with these things. So I've used a similar outline before. I'll do it again. Here's a pictorial outline of the talk. So I'll start with physics, give the existence proof, which again is a common theme, talk about two key functions, 3 ways to build it, and then 2 things to do with it. I'll specifically talk about an evaluation project, and then just one thing at the end that we'll get to. So starting with the physics, this is actually the biggest picture view that we have. This is from the Sloan Digital Sky Survey. We have been able to actually peer out into the universe and see very interesting detail. We have lots of information. And to the best of our knowledge, what's really driving all of this is energy. So again, this is a very big picture view. I'll drill in a little bit. So how about the existence proof, saying, well, it's energy. What allows us to control our bodies to actually capture, store, and use energy? And I don't think anybody will we'll have a big argument about this. It's really our brains as the main control system for that. So what are the 2 key functions that the brain allows us to do? First is to learn and predict the future. So we can actually avoid becoming somebody else's food, and we can actually go capture food. That's the energy part of it. The second function is communicate, so you can actually do these functions a lot more efficiently if you can pass on the knowledge that you've acquired to another individual so you can survive better. Tying this back to the presentation actually Conrad was giving yesterday in terms of the sensory motor genesis of the cortex, in terms of what is really the function of the brain. Again, the key function is to control your body so you can move around in the space that you're in and achieve the goals that you're after. This is one of the best TED Talks I've seen so far, and I'd highly recommend it if you haven't seen it, or if you're not from this kind of a, I guess, neuroscience of motion kind of background. Daniel Wolpert gave a really nice talk about how to frame that question, or how to present the reason for the existence of a brain in humans and animals alike. So how does a brain, a neural structure, really accomplish these functions? So again, this is a conjecture, by no means fully proven, but the sparse hierarchical spatiotemporally encoded representation, processing, storage, and recall is a key feature. The way it appears neural systems are actually representing information is not symbolic representations. It really is a correlated activation of groups of neurons, sparse activation of neurons, and a hierarchical structure that's actually being used to do all those functions simultaneously. You do representation, processing, storage, and recall within that framework. There isn't a separate storage area. There isn't a separate processing area per se. To drill into that symbolic manipulation part of it a little bit further, when we actually do our functions, when we move or when we think about things, we're not really doing symbolic manipulation. We're not solving ODEs or PDEs in our neural system. It really is a different way of representing information and actually going about how to control things. So thinking about that kind of representation, actually very much influenced by Jeff Hawkins' work, hierarchical temporal memory and other sparse data representation, how could you build a neuroinspired or neuromorphic system based on those kinds of principles? So one way is actually doing it in software. You can use clever algorithms and throw them onto the fastest machines you have available and simulate the brain activity. And this is, again, being done in many research groups, many different venues. The other way you can do it is actually you can build hardware that adds certain features to accelerate some of the bottlenecks in that simulation. Again, specialized GPUs, hardware, neuromorphic wafers, and then systems alike. But it's still using symbolic representation at the core of the function. And then the third possible way is actually you come up with a system that does that sparse spatiotemporal representation natively in the substrate itself. So rather than simulating or emulating it, it actually is running with that representation natively in the hardware itself. There is an energy efficiency and speed argument for that third approach, I believe. Let's say taking a neural system example, 10,000 inputs, 10,000 outputs. How do you compute that 10,000 in, generate a single spike, and route that out to 10,000 other things? And actually, Steve Ferber's talk today gave very good insights into how that's being handled in their platform. And if you're really doing this on a conventional electronic system, the only way you can do it is with packet switching. So if you assume a 16-bit address to be able to reach all those nodes, whatever they are, the question is how much energy will that take in terms of encoding that address and delivering that 1-bit payload, or actually, as Steve was mentioning, you can do it with no payload, but just that the address came here is the message itself. So that single bit delivery nominally takes on the order of tens of picojoules and has a time delay of 100x or more on conventional systems. So that example is 1 millisecond of activity takes hundreds of seconds to simulate. Now, again, pointing to the Spinnaker system, there are specialized architectures that you can put together that will do that much better. As Steve mentioned, that has the real-time run capability in the Spinnaker system. It might be possible to do the same functionality in terms of being able to take that one spike and deliver it to other elements in that purpose-built hardware that I was mentioning that actually natively does the sparse spatiotemporal representation. That will require, again, a very different approach in terms of how we construct that system. But the possibility is that that might get down to on the order of tens of femtojoules and 1/10,000th of real time in terms of operation speeds. Again, that's sort of the 1 millisecond spike time in biological time versus much better than 100 nanosecond in optoelectronic devices, which is more readily available, more than readily available. So again, as an example, the Heidelberg platform that Karl-Heinz and colleagues are building, it's relatively, let's say, on the order of tens of picojoules per spike computed, and again, on the order of 1 to 10,000 real time. But again, there are different systems that are at hand that are being built and they're being experimented with. And I think there is a path to go down further in terms of higher energy efficiency and higher integration possibilities for these kinds of systems. So two key enabling concepts. One is massive interconnectivity. in the system, looking at 1,000, 10,000 interconnects per unit element, and self-reconfigurability in the system itself. So you're not running an external program telling what needs to be updated per clock tick. That leads to also an interesting point where there is no software or hardware distinction in terms of how a system like this functions. And the sparse spatio-temporally coded hierarchical representations, again, that seems to be a necessary component to be able to achieve the higher levels of functionality. And again, the three systems I talked about, being able to simulate, being able to emulate it, those two are at hand. They're being developed further. What really is going to be probably the most efficient is actually doing that representation natively in the hardware itself. So this is an architecture that I've been talking about for several years. And if you really squint your eyes and tilt your head, there are 6 layers. There's sort of these blue things that go out and come back in. So this is kind of the gray matter, and this is white matter, cortex-like structure. I usually get that chuckle. So, but really, what we might be able to build is actually systems that have that built-in local interconnectivity, near local interconnectivity, and long-range reach through optical and electrical interconnects. Again, drawing on some of the biological features of cortical columns, the hierarchical temporal memory. And these are potentially built by using the 3D hybrid integration optoelectronics through silicon vias and novel devices, whatever they might be. Again, a lot of this is being leveraged from conventional IC manufacturing, and things are actually readily available in the commercial world, but we're just planning on using them in very unique ways in terms of how they get integrated all together. So again, the key characteristics that an architecture like this provides is the plasticity and adaptability at the lowest level possible in the architecture. So things are self-regulating with local rules, and that massive interconnectivity and fan-out that's necessary for getting the functionality that's needed. So having talked about 3 ways of building it, what are the 2 things to do with it? So again, this is, I had mentioned earlier, that this is a theme and something that's been talked about today here and at other workshops. First thing to do is you can use features of neural computation then to analyze, predict, and control systems in ways that you can't do with conventional computing systems. And then the second thing to do is trying to understand the brain better using these systems as test platforms. So in talking about that test platform concept, I wanted to highlight a little bit of a historical detail here, which I mentioned briefly last year as well. And there are some really interesting parallels here. This is Wright brothers' first wind tunnel. They actually built their first gliders based on the data sets that were available, which were mostly from Europe or wherever. They just weren't getting the performance they were really expecting. So it's like, something's wrong here. So they actually built that bicycle with that contraption on it, pedaled down the road, and kind of looking at that angle said, well, okay, this is actually what that profile, that cross-section is providing us as lift or drag or whatever. And they actually built their own data set to then enable them to build their gliders, their airplanes, with much, much better functionality, much higher efficiency or performance. Very soon after they started doing this, they realized pedaling down the road and trying to read that angle wasn't really all that easy, so they did actually build a wind tunnel. But this was actually the kind of the starting point for that exploration. So that was kind of the test platform they really had to build to start getting the data sets, start understanding what really is happening. So that led to this. In about 70 years, 80 years, maybe actually 50 or 60 years for the bottom left one, but incredible development. I mean, things have gotten incredibly better with the technology, with the tools we have. And I think there is a very close analogy to what we might be able to do in this field in terms of having access to these new platforms that are becoming available and start testing things, start building hypotheses and evolving the software, algorithms, hardware, all in one interconnected loop. So in that spirit, I wanted to mention an evaluation project that we're starting. These are sort of the 4 initial questions that we've been asking potential collaborators, potential colleagues that we'd like to draw into this study. First is, how can we access the hardware, software, whatever system you have, and what are the associated costs and timelines, and especially are there software emulation tools available to run some of the early quick loops of learning. Which algorithms have you used to benchmark this system? And specifically of interest are algorithms related to image processing, because again, there is a lot of knowledge there that we'd like to draw on and to be able to push forward very quickly. Can we get the benchmark results and associated metrics? And lastly, how do these results compare to conventional computing in terms of CPU, GPU? Again, throughout the talks today, we've seen some of this data, some of this kind of comparison happening. We'd like to be able to collect them and sort of and be able to provide a common comparison point for all these different approaches and be able to benchmark them and provide feedback to what the next stage might be. Again, just highlighting the goals, we'd like to be able to use these systems to analyze, predict, and control natural and engineered systems. And again, a common parallel track is we'd like to be able to use these systems to understand how the neural systems might be working. Again, the outcome would be that we'd be able to predict the future in a much more efficient way than what we have right now. Some of the applications, again, if you're thinking about sensor systems, unmanned remote systems, they're actually very common themes. You're limited in the space that's available to you, the power that's available to you. And in certain applications, you have to be able to do the decision on site. You can't really afford time to downlink and then send commands back, be it for robotics or UAVs or whatever that application is. Some of the slightly different applications, talking about big data, cyber, complex adaptive systems. Again, these are huge data sets. We really don't have a good way of getting into the data and making sense of it. And a system like this might allow us to get into there and make sense of it in a much more efficient manner. And connection back to neuroscience, neural interfaces. Actually, some of this work started quite a few years back with a project that we were involved in with colleagues at Los Alamos and several other national labs on the artificial retina. And NeoVision project was sort of being talked about in a similar time frame. And some of our discussions were centered around how does the information get encoded in the retina before it's actually passed down into V1 and other areas in the brain. That encoding scheme is still not perfectly known, but it's an incredibly good test system to start asking some of those questions and trying to make those interfaces function a lot better. And again, connection back to Wright Brothers Wind Tunnel, that's an incredibly good test ground to start getting those concepts worked out. So just wanted to briefly touch on Moore's Law, microelectronics, and what the limits might be. There are 3 reasons that these limits are being reached or actually have been reached. First is physics. Again, a historical analogy here. That's the first ever steam engine, steam locomotive, progressively getting bigger and bigger, and that's actually the biggest, highest power electric locomotive out there. But they're all limited by the same physical feature, and that's the amount of weight you can put on the wheels before you start damaging the tracks. So there is a physical limit, very similar to that in computing. How much energy can you put into a single transistor before you start making errors or causing other problems? And that's, again, scaling, power density. There are a lot of details there that I'm sort of glossing over, but I think the analogy is a relatively accurate one in terms of the physical limitations. The second limit is actually economics. This is a paraphrased quote from Gordon Moore saying Moore's Law will not end because of physics but because of economics. It really comes down to how much effort, resources you have to put in to be able to get the next generation of computing resource. And is that going to make sense for the application that it's being really designed for? And then functionality. This is somewhat of a controversial statement. I'll maybe take the discussion offline for that one. But just talking about symbolic computation not being capable of providing the level of functionality that's needed with the energy efficiency that's required for the next generation analysis and prediction systems. So coming back through these questions, I hope I was able to show you, and actually throughout all the presentations through this workshop, we do need to consider neuro-inspired systems. There are many ways of building these systems, and they're becoming available. And what are we really going to do with them? And again, this is a slide I'm reusing. Hope you'll excuse me for this, but if you've seen it before. What we're really going to do with it is something that Feynman said quite a few years back. And it's this, it's going to be used for entertainment. So I do have a video clip on YouTube from another project. Actually, this is a space project that had a really interesting, I guess, public outreach. And for the interest of time, I won't go through that, but maybe throughout the various breaks, if you're interested, I'd really like to show you guys what form that might take. So with that, thanks again. I'll be happy to answer questions right now.